Hi everyone. This is Jay Shankar. I'm a postdoc researcher at Florida State University, and welcome to the inaugural First Eyes on CMIP Around the World workshop. And this is a science talk session for the Americas Hub, and we are excited to have three outstanding speakers today, Ms. Yiyu Zheng and Dr. Vivek Arora and Dr. Paola Arias. And each speaker will have 15 minutes for their presentation and followed by a few minutes for questions. And to ask the questions, please use Padlet link provided. And let's get started. So Miss Yiyu Zheng, and she's our first speaker, and she's a PhD candidate in the Department of Atmospheric Science at Colorado State University. Her research focuses on climate dynamics, particularly in soil predictability and climate sensitivity in the warmer climate. And she has previously worked as a research assistant at the University of Hamburg and the Max Planck Institute for Meteorology, and holds a master's degree in earth science from University of Hamburg. And Miss Yu, please go ahead when you are ready.
Hello, everyone. I'm a fresh graduated PhD from CSU. So today I'm going to talk about constraining the relationship between sea surface temperature trends in the Southern Ocean and Southeastern Tropo-Pacific over 1985 to 2014. Now, the first question you might have, why do we care about these two regions? And starting with Southeastern Tropo-Pacific, it is a hotspot in climate projections, which can be seen from this figure taken from Dom et al., where they use Green's function to measure how global climate respond to local SST warming. So this red color in southeastern Tropo-Pacific means if you warm the SST here, it would induce a positive global mean radiative feedback. And a positive feedback means it will amplify the forcing applied to the system. So a unit warming in this region would end up making the global climate warmer and warmer. So literally, this region is a hotspot. And it is connected to the Southern Ocean. This figure is taken from Kim et al. 2022, showing the physical pathway that connects the Southern Ocean with the southeastern Tropo-Pacific. So if you artificially cool the Southern Ocean, this cooling signal would be transported equatorward by climatological wind advection, and in the way, it will be amplified by the positive stratocumulus cloud feedback, the enhanced coastal upwelling, and the wind evaporation SST feedback, the west feedback. And then it will finally reach the southeastern Tropo-Pacific and cool the temperature there. Now, this teleconnection is robustly seen after perturbing the model simulations by different means, such as deepening the oceanic mixture depths at Southern Ocean from 50 meter to 500 meter, or reducing the solar flux at the Southern Ocean, or inputting Antarctic ice sheet meltwater into the Southern Ocean. However, perturbations can change the global climate. Cooling the Southern Ocean in these kind of perturbation experiments would inevitably reduce the global mean temperature. So how do we know if the cooling in the southeastern Tropo-Pacific actually comes from the Southern Ocean, or this region's temperature just go along with the global mean temperature really well? I mean, it's hard to tell from these kind of perturbation experiments. That is why we ask, does this teleconnection exist in coupled climate model outputs without perturbing the Southern Ocean by any means? And we answered this question using 42 CMIP models. The model list and their ensemble member sizes are shown in this table. Now, the observations and reanalysis are also included for comparison with model results. And this is a figure showing all the observational products and model simulations we used, as well as their temporal coverage. So our focus period is on 1985 to 2014, shown by this gray envelope here. Now, the physical pathway proposed in Kim et al. 2022 connect the Southern Ocean with Southeastern Tropical Pacific using 4 physical processes: the cloud feedback, ocean heat uptake variability, wind, and west feedback. Our previous work showed that the shortwave cloud feedback and ocean heat uptake are the 2 main drivers in this connection. Therefore, in the study presented today, we only test the effect of these 2 physical quantities along with the SST. Now, the shortwave cloud feedback is calculated by regressing the shortwave cloud radiated effect at top of atmosphere onto local SST using the 30-year historical time series from CMIP models. And the ocean heat uptake is quantified by using net surface heat flux, which would be positive if there's net downward heat flux going into the ocean. Okay, finishing all the technical details, let's look at the tidal connection. The top panel of this figure shows the 30-year SST trend from 1985 to 2014, average over 4 observational products. And you can see there's a cooling trend in South Pacific, especially in the Southern Ocean and Southeast Pacific as we focus on. Now, this similar 30-year trend can also be seen from all 42 CMIP models, but comparing these 2 maps, we can clearly see that models fail to capture the cooling trend in Southern Ocean and Southeast Pacific. Now, this map is obtained using just the first ensemble members from all CMIP models. And you may wonder, what if we use different ensemble members? That change the results? Not really, judging by the stipplings on the map. So the stipplings are obtained by bootstrapping different ensemble members from models available. And regions with stipplings means their SST trends are more affected by internal variability as compared to other regions, which is not the case for the Southern Ocean and Southeast Pacific. So this erroneously positive trend in these 2 regions may unlikely be part of internal variability. Well, are they connected? We use a cross-model regression analysis to answer this question, which is shown here. So the dots are individual CMIP models using just the first ensemble member, and other shape of markers with black outlines are observations or reanalysis. The straight line is the linear regression fit using just the dots, and the uncertainty range represents the effect of internal variability obtained after bootstrapping different ensemble members. The R-square value, this one, is obtained using the regression on using just the first ensemble member, and the values in brackets represent the 95% confidence interval and the median of the bootstrapped distribution. So from this figure, we can see that models with larger warm trend bias in Southern Ocean as compared to the observations also have larger warm trend bias in Southeast Pacific. Can we say they're connected now? Well, you might notice that I left a part of information unexplained from this figure, which is the color of the dots, which represents global mean SST trends. So that says models with more warming in Southern Ocean have more warming in Southeast Pacific, but also have larger warm trend bias in its global mean SST trends. So that suggests these 2 regions looks connected because they warm together. How about removing the global mean SST trends from the local trends? Well, due to the time limit here, I exclude those figures from this talk, but the normalized SST trends in these 2 regions remain positively related, showing a rather robust relationship. Next, the physical processes with the shortwave cloud feedback showing the first. So in regions covered by stratocumulus, like off the west coast of South America, this feedback is positive, meaning that if we increase the local SST under this stratocumulus cloud, it would reduce low cloud cover, thus less shortwave radiation can be reflected back to space and more reach to the ground, which further increase the SST. And by comparing these two maps, we can see that models underestimate this cloud feedback strength. And could that be part of internal variability? Well, judging by this bar plot, where the gray bar shows the first ensemble member, the dot shows other members, and the lines shows observed cloud feedback, we can see that at least 90% of models and ensemble members underestimate this cloud feedback, meaning that this underestimation is unlikely due to or a part of internal variability. Now, what is the hypothetical effect of this positive cloud feedback on the Southern Ocean, Southeast Pacific teleconnection? Well, if we have an SST trend signal transported from the Southern Ocean equatorward, a strong positive feedback would strengthen this positive SST trend, making sure it can reach the Southeast Pacific and thus making a strong connection between these two regions. So basically, we expect a positive effect of cloud feedback on these two regions' teleconnection. Then, ocean heat-up variability, which is defined as the standard deviation of the net surface heat flux time series. Now, the spatial pattern of ocean heat uptake's variability seems alike between models and observations. However, models also underestimate this ocean heat uptake variability off the west coast of South America, and it is also unlikely a part of internal variability, as shown by this bar plot. Now, again, what is the hypothetical effect of this ocean heat uptake variability on the Southern Ocean Southeast Pacific teleconnection? So if we have a SST trend signal transported from the Southern Ocean to the tropics, a strong ocean heat uptake variability means adding more noise to this SST trend, thus distorting this SST signal and weaken the relationship between these two regions. So we hypothesize a negative effect of ocean heat uptake variability on this teleconnection. And let's test our hypothesis. This slide shows the technical details of obtaining the effect of cloud feedback on this relationship. So first, we rank models based on cloud feedback averaged over a box of West Coast of South America. And then we select 15 models to form a group, as shown by the dots in green. Now, inside this group of models, we do a cross-model regression between Southern Ocean and Southeast Pacific SST trend, which gives this green regression fit and an R-squared value of 0.4. So we measure the strength of the relationship between these two regions using the R-squared. And my apologies for this formatting issue. This should be an R-squared fitting in this blank. Now, since we have 42 models in total, we can select another group of 15 models and repeat the whole process again. And unlike the bootstrapping analysis where models are resampled randomly, our analysis would be a running grouping of models based on their order of the cloud feedback. So we could dump one model and include a new model to update this grouping, as well as updating the mean cloud feedback and the R-squared. Now, these models in pink represent the last group with the highest mean cloud feedback and an R-squared value of around 0.6. Now, because we don't want our result to be just by chance due to internal variability, we bootstrapped different ensemble members, repeating this whole process for 5,000 iterations and getting the R-squared and cloud feedback from all different groups of models, as shown by these giant, enormous breakdowns. And finally, we do a regression fit to all these possibilities, and the black regression line means if a group of models have strong cloud feedback, they would also have a strong relationship between Southern Ocean and Southeast Pacific. So this is a positive feedback, a positive effect that fits our hypothesis. And now combining the information that models underestimate the cloud feedback as compared to observations, If we have a group of models that have a mean cloud feedback lying inside this observational range, then we would expect a stronger relationship between Southern Ocean and Southeast Pacific SST trends. So to put it in a simple way, models underestimate cloud feedback, pointing to underestimated relationship between these two regions. Well, for ocean heat uptake variability, going through all the grouping and bootstrapping processes, it has a negative effect on this relationship, which also fits our hypothesis. But since models also underestimate this quantity, that points to an overestimated simulated relationship between Southern Ocean and Southeast Pacific. So we have opposing constraints from these two physical processes. Now, wrapping up, we show that this teleconnection exists in a historical climate when both regions show erroneously positive SST trends. And what's important about this conclusion is that before, in previous studies, they all proved this teleconnection by perturbing the model. And in our study, we say, well, it exists in coupled model outcome. And that points us to a conclusion that because if Southern Ocean warm in the next few decades, that also points to a warmer Southeast Pacific. And given the hotspot role of this region, we would expect a warmer climate, given this intrinsic teleconnection. And we also show that the two main physical drivers, the cloud feedback and ocean heat uptake, have opposing effects as well as opposing constraints on the simulated strength of this relationship in climate models. And we argue that both of these factors need to be taken into consideration when talking about improving this teleconnection, improving in simulating this teleconnection in climate models. And that's all from my side. I'm happy to take any questions.
Thank you, Miss Yiyu. And now we welcome any questions. Maybe one quick question, and then we will go to the next speaker, and we can have more question in the last.
Mhm.
Maybe I can ask one quick question. Is there any reason that you chose 15 model for your ensemble mean computation slide level, or you just that was a random 15?
I test different choice, like from 5 to 30 models, and 15 is just an optimal choice that it does not have too many models in one group. So this running grouping thing would have some decent sample size. And this model would also not be too few, like 5 models, that make this cross-model regression noisy. So 15 model is like an optimal choice within a range that we tested.
Okay, thank you. So
Thanks.
So we have our next speaker, Dr. Paola Arias, and she's our second speaker, and she's a climate scientist and professor at Environmental School of University of Antioquia in Colombia, and her research focus on climate change and hydroclimatic modeling across Colombia and South America. And Dr. Arias is a lead author of the IPCC Sixth Assessment Report, and she's also a member of several international scientific panels, including the GEWX Hydroclimatology Panel and WRCP's My Climate Risk Initiative. Dr. Arias, please go ahead when you are ready. You are not audible. Yeah, good.
Thanks a lot for the invitation to this workshop. Today I'm going to be more from my experience. The talk that I'm going to give is not like a particular scientific topic, but more how our research group in Colombia have been using the CMIP simulations and how has been our work on this regard. So that's what I want to share with you. So please, are you seeing my slides?
Yeah, you may move to the presenters mode.
Yeah. Mm-hmm. Okay, so as I mentioned, what I want here is to share our experience as a research group in Universidad de Antioquia in Colombia using CMIP models. So just to start, I did my PhD under the supervision of Dr. Ron Fu in the United States. And then I did a postdoc with Maisa Rojas in Chile. And during my postdoc, I tried to understand how the CMIP models by that time were representing the lengthening of the Amazon dry season. However, I didn't publish anything on this. However, I could start working on publishing on these topics later with my students in Universidad de Antioquia. So the first graduate student, no, actually undergraduate student that I had was Juan Pablo Sierra. At that moment, he was finishing his undergraduate program in environmental engineer. And we started with only 7 CMIP models because we didn't have much technical capacities to process a lot of data from CMIP models. So we started very modestly working on how these models simulate precipitation in the region. And surprisingly, this has been a paper that has been quite cited in the region. And it was a very good step, but it was a very modest step because we didn't have much of the capabilities that we needed. But then working with him, a second in his master, actually after his undergraduate program and after in his master, he worked with much more models. In this case, he used 37 CMIP models, and he was more focused on the Chocó low-level jet, which is an important circulation feature for Northern South America, particularly Colombia. And before he was leaving to France to pursue his PhD, we work also with paleoclimate simulations, particularly those in PMIP, trying to see like past, present, and future of the Chocó low-level jet. So this was like the first steps using CMIP in our group with Juan Pablo as an undergraduate and then a graduate student. But by fortune, our CMIP gang grew up and we start having more students. So that was the case of Joseph. Joseph worked on the entire Latin American region, particularly Central and South America. And he evaluated the performance of different CMIP 5 and CMIP 6 models, a large set of models. And he was looking for climatological features associated with temperature and precipitation over these regions. With him, we started comparing CMIP 5 and CMIP 6, and we had like a larger machine, let's say. We were able to work with more simulations and start asking different questions. And then Laura Villegas came in our group as an undergraduate student. Now she is doing a master in Costa Rica, and her work has been one of the most influential works that we have done, because what she did was to take a look into the third national communication of Colombia to about climate change, where the country proposed a climate change scenario, and she found very strong and important inconsistencies, because in particularly what the government did was to do a mean of the 4 RCPs as a national scenario, which makes no sense. So what we did was start looking into the different uncertainties and inconsistencies that this type of approximation gives. And at the end of the undergraduate thesis that Laura developed, we have this article in a national journal. It's from the National Academy of Science in Colombia. It's in Spanish, but this was very, very strong because we had more than 30 Colombian scientists being part of this, like as a declaration of academia in Colombia asking the government to provide more reliable national communications. And then with Laura and Joseph's experience, we published this paper in English, but in a journal, a home journal in our institution, that was actually in the 100 version of the journal. And there we were seeing like climatological features in Colombia simulated and projected by CMIP 5 and CMIP 6 models. So we could do something at the national level, doing something on this regard using a large set of models and even Cortex models. So then we started looking into a different perspective, not only looking into climatological futures of precipitation and temperature, and then with Maria Lisette in her master, undergraduate and also master program, we work more on how could be the changes in atmospheric moisture transport in Northern South America associated with different scenarios of climate change. So what she did was that she used 11 CMIP 5 air system models, and what she did was running a particular semi-Lagrangian model for moisture tracking, that is DRM, using these outputs from the 11 models and seeing how are the possible changes during this century in atmospheric moisture sources and sinks in the region. So this is a different approach because it's not only looking into the normal or typical variables, temperature and precipitation, but looking more into the mechanisms associated particularly to precipitation. And among these mechanisms is the Orinoco low-level jet, that is another circulation feature in the region. And then Isabel, another master student, did her master. She recently graduated using a large set of CMIP 6, but also CMIP 5 models looking into the Orinoco low-level jet. And here we were looking not only in simulations, historical simulations, but also looking into the future, possible changes on their different SSPs and RCPs. And then, like working in a more extended way, Joanna, she was one of my first undergraduate and master students. She did a PhD in University of Los Alpes in Grenoble, and I was one of her co-advisors. She worked on understanding precipitation mechanisms behind precipitation in different regions in South America. Not now that much in Northern South America, but more the Altiplano and the Amazon region. So as a result, she also used different CMIP 6 models, but her approach was more focused on mechanisms, not only on the spatial patterns, the seasonality, but more on the mechanisms that control precipitation over these regions in particular. And more recently, we are working more on extremes, and that is where Juliana takes an important role. Juliana started as an undergraduate student, and actually she has a paper on the review in climatic change regarding how the PMIP 3 and PMIP 4 models simulate ENSO flavors, Modoki and canonical flavors, and their teleconnections under the last millennium forcing. And now in her master, she's currently working on compound, dry and hot extremes in Northern South America. Actually, it's total tropical South America. It includes also the Amazon. So this is a new avenue of research that we are focusing now also on extreme events, in this case in dry and hot compound extremes. Also regarding extremes, one of our recent work that is still not published, but Manuel is working on this, is Manuel worked on the attribution of the intensification of the water cycle in tropical South America, particularly in northwestern South America, where there is an increase in wet extremes, and also like the Amazon and the Orinoco region, where there is an increase in dry extremes. He has been working on this. He's working on his paper, and this is actually our first effort on attribution in terms of climate change in the region, particularly for the water cycle in terms of their its extremes, not only the mean variability. And in this line, like thinking also another approaches, Juan Pablo has been working on a pseudo global warming type of storyline to understand what could happen with a mesoscale convective system that triggered like 300 or 600 landslides, and then a huge debris flow in Mocoa, in the Amazon, Andes Amazon transition region in Colombia. which had like very, very terrible consequences. So he has been working on this approach of storylines based on pseudo global warming using the CMIP 6 models that reaches fastest the 2 degrees Celsius global warming level. He's in this moment he's waiting for the defense of his master thesis, and he's working on his paper. So not only inside the group, but also outside the group. This is this just came out this week, I think. This is our most recent work, and I think the most ambitious work we have performed using CMIP models, because what we did was using 50 CMIP 6 models to evaluate like about 30 features of atmospheric circulation, but also boundary conditions for the entire South American continent, particularly thinking that this could be useful for regional modelers to choose the global model, like could be more suitable to force their regional simulations. So this is for the entire South America. It took us about 4 years to complete this work. And it was the result of the collaboration with scientists in Peru, Argentina, Chile, Brazil, Ecuador. So this has been a very, very nice work, because this really shows like the integration in the region in terms of the analysis, in this case of CMIP simulations. And we also have contributed to world weather attribution, particularly in the detection and attribution of a heat wave, and also a drought in South America, more located in Argentina, not that much in Colombia. And for this type of protocol of detection and attribution, it relies very heavily on CMIP simulations in general, Cordex simulations, CMIP simulations, high-res MIP simulations. So this is another avenue of work that has been very, very active during the recent days. So I just wanted to give a perspective of how a South American research group has been working with CMIP. And here I want to really give the importance and give the huge attention to the early career the researchers as students, but also as professionals working on these areas, because without them this wouldn't be possible. And this is a workshop that is dedicated to early career researchers, how they can be involved in the CMIP community. So that is why I wanted to give this presentation instead of giving something focused on a particular scientific topic, because I think it is important to have the motivation. I started as an early career scientist when I started working with CMIP. Now I have more experience, but I still learn a lot. And I think these type of workshops are very important, because I think you can learn more about what is CMIP, what is this useful, how can I be involved, not only as a modeler, but also as a user. I am mostly a CMIP user, not a CMIP modeler. So I think this is very important also to give, in these very difficult times that I think we are facing. Is very difficult to find a job, a permanent position, even to find postdoc positions, etc. To also to give the strength to the early career scientists that there are a lot of possibilities, and particularly in the CMIP community, I think there is a space for many, many, many active people. And that's why I wanted to end my presentation inviting you to join the early career CMIP gang around the world, because I think it is very important to give a fresh look of the simulations. There are a bunch of simulations that we even don't use, to be honest, in the world of CMIP, and in general in the world of the model intercomparison projects. So I think it's important also to give the perspective that all of this is possible because the engagement of many early career scientists. So that's how I wanted to give my presentation for this workshop. Thank you.
That's great. That's great presentation and great motivation as well. And I appreciate the effort in bringing up all your research activities so far in related to the CMIP and in your research group. And thank you very much. And I would like to ask a couple of questions, and we have a few minutes to have some questions. Please go ahead if anyone have any questions to Dr. Paola.
I've got a question if you don't mind me asking.
Yeah, please.
So that was really great, that presentation. Thank you. So I guess my question would be, being as your group has used a lot of the CMIP 6 simulations, for example, with your work, what are you looking for out of the forthcoming CMIP 7? Are there any particular MIPs that you think would be very beneficial to this, for example, South American region in terms of the research?
I think it is important to consider that this region is particularly modulated by topography. You know that the Andes is a very narrow mountain range, and here in Colombia it splits in 3 branches, so it's even harder. You know, so it's very, very difficult that the models at a very coarse scale are able to capture many of the different scale features that we have in our climate patterns, not even weather patterns. So I think something that I really would like to see is, for instance, how the improvement in horizontal resolution and this a step going to more like CP simulations could improve in the region. But something that also is for me very worrying is that, of course, these regions in general in the global south are very limited by the observational data, right? So of course models are biased if there is not enough observational data to also validate models to see if the models are performing well or not. So I think there are different things that I am very keen. Sometimes I'm very critical also on the CMIP in terms of, okay, we have a bunch of simulations that are very expensive to run, take time, but you see that many people don't look at most of those, you know, like it's only like the typical experiments that we use. So also how to make use of these different MIPs that exist, that we could really learn from that, and also maybe that would be something that could be also strengthened with regional simulations, not only global simulations, but how to also improve the regional simulations, because there is still a big room of improvement and learning in terms of these simulations. So that's my view on the next CMIP phase.
Thank you.
Thank you. So with this, we will move to the next speaker, and we will receive more question in the next, after the presentation. And so our final speaker is Dr. Vivek Arora, and he's a research scientist at Environment and Climate Change Canada. His work focuses on modeling terrestrial biogeochemical processes, and particularly the carbon cycle and understanding land-atmosphere interaction using Earth system models. He has contributed to major international assessments, including the IPCC 4th and 5th assessment reports and AMAP. And Dr. Arora, please go ahead when you are ready. Thank you.
Can you hear me? Oh, you're muted.
Yeah, we can hear you. Yeah.
We can hear you. Please go ahead and share the presentation.
Okay, I'll share my screen. Sorry, I haven't used WebEx before. I was hoping to share my entire screen quickly.
Okay.
Here, yeah, there we go.
Yes, now you can open the PPT.
Okay.
Maybe the presentation mode. Yeah, perfect.
Yeah.
Go ahead.
All right. Okay. All right. That was a very good talk by Paola. And I'm going to talk more about science. I work at the Canadian Centre for Climate Modeling and Analysis. It's part of Department of Environment and Climate Change in Canada. I want to acknowledge CMIP and C4MIP. I'm a co-chair of the Coupled Carbon Cycle and Climate Model Intercomparison Project. along with Chris Jones and Tatiana Iliana. And it's been a very useful experience. And since I work at a climate modeling center, I am also involved in developing the land component for our Earth system model. It's been a great experience being part of a climate modeling center. You get to see the big picture. I know, of course, there are a lot of users who use data from the climate models, but being embedded in a climate modeling center helps to see the bigger picture and how difficult it is to make your model work. Okay, so we all love metrics. We have NASDAQ, we have Dow Jones, we have all these other indices. We like our metrics. And in the climate world, of course, we have these two temperature-related metrics, which we use often. There is the equilibrium climate sensitivity, which is the warming you would get if you were to double the CO2 instantaneously. And we do this, this is one of the standard climate modeling experiments. There is also the transient climate response, which is if you keep increasing CO2 at 1% per year, and that's your 1% CO2 experiment. And then when the CO2 doubles, what's the temperature at that point in time? And that's the transient climate response. And equilibrium climate sensitivity is higher because you let the temperature come into equilibrium. That's why you can see the range here from CMIP 6 models. About 2.4 to 4 degrees Celsius, and it's higher because the temperature comes into equilibrium, higher than the transient climate response. So, and these metrics are helpful. They have no real world application as far as I know, but they do serve a very important purpose. And one of those purposes is it allows you to compare models and see how different the models are in terms of their temperature response to greenhouse gases. I'm going to talk about metrics in the context of the carbon cycle because that's what I've been involved in, and I want to raise some challenges, and I'm hoping as early career researchers, some of you will probably pick up this problem and try to address it. If I were to try to summarize carbon cycle in two equations, this is how I would do it. So if we put emissions in the atmosphere, both land and ocean take some CO2, they take up carbon from the atmosphere. So the rate of change of carbon in the atmosphere is emissions minus the flux into the land and flux into the ocean. And once you know, and of course, all of these are functions of time. Once you know how CO2 is evolving, temperature change at any time is CO2 at that time minus whatever the initial concentration was. So that's your temperature change. And climate models are able to run this kind of setup in two modes. They can run it in concentration-driven mode, where the concentrations are described. So if the concentrations are prescribed, which means dC by dt is prescribed, land and ocean are doing their thing. They're taking up carbon, say in response to increasing CO2, you can figure out the emissions. So you can diagnose the emissions back, or you can run the model in emissions-driven mode, where you put the emissions into the atmosphere, land and ocean again wants to increase carbon in the atmosphere, and then you find dC by dt. So you find the CO2 pathway that the atmosphere would take given a pathway for emissions. So models can be run in both these two modes. And as a modeler, I can tell this arrow. So I'm a land carbon cycle person. It took me 5 years to do this arrow from scratch. So early on in my career, I developed a carbon cycle model for the Canadian Earth system model on land, and it took me 5 years to do this arrow. And of course, on the ocean side, it's even more tricky. So that's the summary of how carbon cycle works. Now, we also know that of all the emissions we have put in the atmosphere, only about half have stayed in the atmosphere. The rest have been taken up by land and ocean. And of course, probably you have seen this figure on the left-hand side from the Global Carbon Project. And you can see on the top, you have the anthropogenic emissions, both fossil fuel emissions and land use emissions, and